All right.
Yes, it is. I can't. You can see
This is in chapter 7. All right. Let me go ahead and kind of set this up for you. Let's draw our kidney bean rotating about the ground. And I know that I had before, I had omega. So I had omega going like that. And if I chose a point along the object like that, let's say, then what I would do is this vector up to here would be RA. And if I draw my coordinate system here, X going off to the right, and therefore Y, which is the imaginary axis, would be going like that. And I would have, if omega was going like that, then this right here would be the velocity vector. All right? Perpendicular to that vector. And this vector right here, the position vector, is theta A. And I could also, if I wanted to, put my unit vectors in here. So this unit vector here would be B to the J theta A. And if I rotated that 90 degrees, I can simply take this and the unit vector this. Is found simply by taking a J and putting it out in front. All right? So I say if RA, which is a vector, so it has magnitude and direction. If I take that vector and I differentiate it with respect to time to get velocity, I get RA omega J e to the J theta A. And that's what we saw before in the previous chapter, or actually chapter 6, I guess it is. If I take this here, one more step and take the derivative of the velocity, then I get, so I'm looking at this, I get RA, the change of omega with respect to time, J, so I'm just writing this here, e to the J theta A, plus, now if I take, so that is that component, the omega derivative with respect to time.
That J isn't supposed to be negative in there, that exponent?
No, it's not.
Okay.
That's a scuff mark to my pen. Yeah. So this right here, if I take the theta component, then I have j squared RA omega e to the j theta a, but then I have to account for the change of the angle with respect to time. Okay? So that's the complete derivative. And if I note that I define alpha, which is the angular velocity, I'm sorry, angular acceleration. Is equal to the change of angular velocity with respect to time. And I also note that omega is the change of theta with respect to time. And I also note that j squared equals -1. Okay? So if I do that, I can say that the acceleration of A here, I'm writing this again here. If I take that, I can write that as RA alpha j e to the j theta A minus, because I got the j squared here, minus RA omega squared e to the j theta A. Okay? So I'll rewrite this as RA j alpha minus omega squared e to the j theta A. And the reason I'm doing that is I want to break out these components here. So this component here is the tangential component. And this component here is the normal, what we call the centripetal, normal or centripetal. Toward the center. So that's the toward the center component, and I'll illustrate that in a second. So let me just kind of finalize this. So acceleration of A equals A tangential plus A normal. All right. So let me see if I can find something to swing here. Okay. Let's look at this. So if something's rotating, all right, so if something's rotating like this here, and I actually hit this on something, that force that I hit that with is the tangential force, because that's the tangential component of the acceleration. Now, as I'm swinging it, I'm actually, if I don't have my fingers fixed here, the thing is just going to fly off. And whether you know it or not, you're constantly pulling back on this thing towards the center of rotation. So that normal component, or centripetal, that's towards the center, is from the outside going towards the fixed location, which in this case is my fingers. So that's why there's a negative sign here, because that's towards the center, and 90 degrees from that with the J is the tangential acceleration. So that's where those two components come into play.
Why did you square the omega?
Because the geometry, the math says to square. Because if I take this here, this omega times the d theta dt is omega. So I got omega times omega. So the math dictates how I'm getting omega squared.
Because it's going down.
And it's going down towards the center, right? That's why the minus sign, this j squared turns out to be negative, and that's why the minus sign appears right here, because it's toward the center. That component of acceleration is towards the center always, okay? If it wasn't there, the thing would just fly off. If I draw this out here, I'll show you what it looks like. So if we want to look at the total acceleration here,
Can you zoom out, please?
I looked at this right here. And say I have my point A here. Draw a line from the center of rotation up to A. And this component here would be my normal component. All right. And then this component here if my alpha was going like this, so if alpha is going like this would be my tangential component. If alpha was going the other way, this would be going off like this, but it has to be 90 degrees from here. And my total component would be something that looks like this here. This is, just by coincidence, it looks like it's going straight down, but it does not necessarily have to be like that. So this is the total acceleration that's going like that. All right? But regardless of omega being positive or negative, your component, because you're squaring it, it's always going to be a direction going like this because of the j squared, so it's always going to be towards the center. So your omega can be like this or like this, and it's going to give you the same result. All right, let's go ahead and, so that's the brief intro to how we're getting acceleration. Let's go ahead and apply it to